have been talked about a lot of 3D printing process, but actually many of those process for their machine, they share the common mechanical elements. And let's look at them. So the objective of this lecture is to let you guys become familiar with the mechanical hardware used in most 3D printers, and you should be able to do some basic calculations needed to control the motion in the 3D systems, especially the distance and the speed. The printing head or the printing bed should move. So the brain of a 3D printer is usually the microcontroller. And as you can see here, it here shows a typical example of a microcontroller. And also there are a lot of open source microcontroller. For example, the one we use in our lab session, the PUSA. It utilizes one of these widely used microcontrollers. So you can see there are several modules which are essential to the 3D printer, like the ones shown here to control the extruder motors. It has two motors. That means it could print the multiple materials or multiple colors. And also here, the one to control the Z axis and the one controls X and Y. Also power supply here. There's a module to control the heat beat, and there are some ones control the extruder heat, and so on and so forth. So usually this kind of microcontroller will cost less than 100, but it can do a lot of work. Besides the basic functions of the 3D printer, you could include the Wi-Fi, Ethernet, or support a LED display or some webcams output. It's all integrated on this board. Another very important component will be those sensors to detect whether when the item moving along the axis has reached one or the other end of travel. So when you do the lab sessions, you will notice that for the Prusa machine or even the Onyx machine. So basically, the first step when you start a printing, that is to home, right? To go back to the original position of the printing head. Basically, that is for detecting what is the initial position for the printing, such that it will know how to move the printing head. There are different types of sensors to figure out whether it touched the end of one axis or not. So for example, this one is a mechanical based sensor. So as you can see here, when when this is pressed down to here, this circuit will be got through, and there will be a signal generated such that you know there will the y-axis, the item has moved to the end of the printer along one axis. Also, there are some optical bits like the one shown here. As you can see here, so here is a from here there will be a light source and there will be a light produced shoot from this side to this side, and here there's a direct detector. So as a normal, when the item hasn't moved along and hit the end, this circuit will have a signal that there is a light, right? But if it hit here, it reached here, the light will be not there, and then this circuit will not have the light signal anymore, such that you know it reached the end of one axis, right? Also, there are some magnetic based ones based on the Hall effect. For the sensor states, there are two different types. One is NO or NC. So NO means normally the sensor is open. That means the voltage in the circuit is um, is a uh, uh, is above certain threshold. Usually in the circuit we set 3.5 watts. Uh, I mean 3.5 voltage as the threshold. That means if a sensor has an NO over there, that means normally it is on and has a voltage above 3.5. So similarly, if a sensor is in the normally closed states, that means normally the circuit in their circuit in the sensor circuit, the voltage is below certain threshold, usually below 1.5 V, something like that. Also, the temperature is very important for many 3D printing process. So there are widely used three types of sensors for detecting temperature. One is thermistor, and sorry, basically it utilizes the semiconductor resistor, and it detects the resistance change in order to find out the temperature, because the resistance change is a function of the temperature. And similarly, the resistance temperature detector is not it does not use a semiconductor. It use the metallic part. Um, so both thermistor or the RTDs, they detect a relatively lower temperature. For higher temperature, usually above 300 Cs, you need to use the thermocouples. So thermocouple is something like this. It has those twisted metal together, different metals actually together, and when the temperature change, uh, there will be a different uh, resistance change as well, and you could detect that signal and tell what is the temperature over there. So this word PID actually stands for the proportional integral deviation control algorithm. So in this temperature control of the 3D printer, you do not want to use the simple strategy, means you give the current and the temperature is rising, right? Because for such a simple strategy, you will easily have the temperature overshooting. Means, for example, you want to hit the printing bed to like 200 C, but probably you will end up have a temperature 220, 210. So that's why you need a more complicated control algorithm, this PID-based one. And I don't want to go to detail of this, but just let you know, with this PID tuning applied, you could have a very robust control for the temperature. So for the positioning resolution, that is the smallest distance that you could ask the system to move in any direction. And that is very important in the 3D printing process, because it will affect the printing resolution, the accuracy, and the robustness of the printer. Um, um, and I will introduce what are the factors in this positioning resolution in the later slides. Also, for the control strategy, there are two types. One is open loop, another one is closed loop. For the open loop ones means you just ask the you just give the signal and move the motor, but you don't know whether it will reach what you expected or not. That's the open loop. But for the closed loop control, meaning you will you will keep on monitoring how far, how much the motor moved, and based on what you have, what you measured, you could change, do the adjustment, change the motion of the motor. But unfortunately, current 3D printers usually only utilize the open loop. There are no closed loop ones. That means if something goes wrong, there's no way to correct it, right? So first of all, for the motion, the main drive of the motion is the motor, right? The different types of motors. There's a DC motor, which is the simplest one. You apply a voltage and the motor turns. And the speed of motor is proportional to the voltage, and that's it. The other two types, which are more complicated, the servo motor and step motors. Actually, most of the 3D printing system utilize the step motors. So the step motor will have, from its name, there are steps. So that steps will decide the smallest distance the printer can move. The servo motor actually is even more complicated, and it has an encoder which could give you a feedback control for the motion. Of course, the cost for a servo motor is higher than the step motor as well. Sorry. The position resolution actually is controlled by the steps of the step motor. So basically, each step of motion by the motor represents the smallest rotational incremental achievable by the motor. Means you could probably have a smallest rotation like 1.8 degrees per step or 3.6 or something like that. But you cannot have some very small number like 0.00001 degree per step. That's not possible. So just give you some idea about this. So for the step motor, basically, as you can see here, there are a different set of electromagnetic over here. So by energizing or de-energizing each of these electromagnetic, you could control the motion precisely and let the rotary part rotate by, like in this case, 3.6 degrees per step. Right. So in other words, it will take 100 steps to make a full rotation for this motor, right? And there's another very interesting concept is called the macro stepping. So that is something like you could have even smaller rotation than the steps of the step motor have. And how we could achieve it, let's look at this video.
The stepping motor can be controlled by a micro-step drive technique. The micro-step is a technique to electrically segment the step angle for reducing the vibrations and noise of the stepping motor. Now we will see the operating principles using the 90-degree step model. The power of the magnetic field where the electromagnet is generated is in proportion to the current size flowing in the coils. We will turn on the 9/10 current in the S1 coil and the 1/10 current in the S2 coil. It is drawn a little towards the S2 coil by the amount corresponding to the variance, and then stops rotating after a little. If you change the ratio of the currents, you can drive with a smaller step angle than conventional step angles. It is possible to break the basic step angle of 0.72 degrees down to 1/250th, which is 0.00288 degrees. This technique allows you to use a minute angle feed for smoother operations. This is ideal for applications which prohibit vibrations or noises, or require a minute angle field. This is also good for applications to reduce uneven rotations at low speeds.
Okay, as you can see here, this macro stepping is achieved by precisely control the relative ratio of the uh, two magneto, electromagnetic magnetics, such that you could have even smaller steps, even smaller angles in the steps. Um, so for example, if a motor has a 200 steps per revolution, um, how many degrees would, oh, I think we should let's introduce the micro step further and then go back to the question. Okay. So first of all, this macro stepping basically could be very small. For example, here shows a 1/22nd microstepping, means you can rotate the motor 1/22nd of a step when the microstepping is used. So that's a really small number, right? Uh, but uh, but because when you are doing the microstepping, the power is much lower than its normal power. So that means if there's some load applied on the motor, you cannot rely on the microstepping for the resolution. For the positioning accuracy, because it could affect the precision of the macro steps. So that's why for the positioning accuracy, do not rely on the macro step resolution, right? Okay, another interesting question is if you have 200 steps per revolution, then how many degrees will the motor turn per step? So basically, if you have 20 steps per revolution, 200. That means for the one revolution, um, 360. You want to divide it by 200, right? And then it gives you 1.8 degrees um, per step. Then you will have a uh, degree per step. And also, if you have a degree per step, then you could tell how many steps you have per the revolution, just to do the exact inverse way of this calculation. Right. Some other informations like the stepper motor size. So based on the NEMA, National Electrical Manufacturer Association, there's a standard for the motor size, and based on its name, you can tell the dimension of the motor. For example, this NEMA 23 has a mounting face width of 2.3 inch. You basically just divide divide this number by 10, then you will have the size. So sometimes for the closed loop control, you want to have the rotary encoder. So for the rotary encoder, you could do a measurement about the motor. Actually, how many degrees this motor actually rotate. And there are different ways uh, for the rotary encoder. And let's look at the optical one. So the optical one is something like this. It has such a disk, and it is it is mounted onto one end of the motor, and on each of the disc, you would see this kind of small slit. Actually, maybe I drew too large, but it is really small actually. And we are looking at the front view of this encoder, and if we look in this way, in a side view, basically what you will see is something like this. So for example, this is the side view of this slit, and you will have some detector and emitter like this. So this is emitter and this is detector, and the light will be travel from this direction to this. And if this light travels through this slit, the circuit attached here will have a signal, and it tells, okay, basically the light travels through this slit. So let's say if this encoder is rotated by a certain angle, um, the light may not be able to travel through a slit. And we have so many slits, and there will be different states for each of the slits on and off. And by combine those different states, you will have a code. And this code could tell you how where the motor is is rotated to. And here that gives you the information about the rotation of the motor, and you could utilize this in the control strategy. Um, so let's look at the motion stage. As you can see here, a 3D printer typically have one or more axes, and here shows a 3-axis one. You have the left to right direction in the x-axis, and the front back, the y-axis, and up and down, the z-axis. So in this case, this is the x, this is the y, and the up and down are the z, is the z. So many of these XY station use the timing belt, similar as, I mean, we can see in the Pulsar machine, we have the timing belt as well. So the timing belt is something like this, right? And if you look at this, it's even clear. So the timing belt will drive will transmit the rotation of the, the timing belt together with this pulley will transmit the rotation of the motor to a linear motion. So as you can see here, there's a real systems. Basically, the bushing attached with another part will slide onto this reel. So what are the critical concerns for this kind of reel system? So that is, you definitely want both the left and the right reel. They are always parallel to each other. Otherwise, there will be some resistance during the motion. Right? Also, over here we have the bushing, and from the color of this bushing, we can tell it's a in bronze material. And this is so-called the self-lubricating bronze. So for this kind of bronze part, um, it's it's porous. It has a porous structure. I mean porous structure, and in this small pores on the surface, I mean the inside surface of this bushing, there are oil over there, such that when it is self-lubricating. But if we use such kind of lubricating bushing uh, to a powder-based system, that could be a problem because the powder will get into uh, these small gaps and make this self-lubricating bushing um, failed, and that's a big problems for such kind of uh, bushing systems. Also, the rails usually are made of stainless uh, steel, and also you need to polish it as well because you definitely want to minimize the friction between the bushing and also the rail. Why stainless steel? Because if there are some rust over there, it will also bring the resistance to the motion. So let's do some calculation for this belt and pulley systems. As you can see here, the pulley will be attached. One of the two will be attached to the motor. Let's see this one. So it could rotate in this and or this. I mean this direction, and together with this timing belt, uh, uh, the bushing and also the platform will move, will be driven by the motor. And we definitely want to have some understanding about the velocity of this, like this black dot. It could be where where the platform is or the printing head is. Um, so let's look at some details. For example, if you have you have a diameter of this pulley dp, for each rotation of the motor, how far will the black dot move? So as you can see here, we have let's see, we have the this is diameter, and you definitely want to compute the circumferences. I mean circumference, and that is the pi dp, and also um, that is the how much this pulley travels per revolution, and that is how much this dot moved per revolution. And if we know the again the pulley diameter dp, and for every one rotation of the motor, then how many rotation will the pulley make, assuming the motor is direct attached to the pulley? So with this assumption, that means if the motor rotate one is rotated one rotation, then the pulley is also made one rotation. Another question: if the motor turns n revolution per minute, then how fast is the drive pulley spinning per in the unit millimeter per second? And if we use the analysis of unit, we could have the answer. So we have the n revolution per minute, and each of the minute has 60 seconds. Also, per revolution, uh, the pulley travels pi dp millimeter, and to put them together, you will have the how fast the pulley spinning millimeter per second. So if you want to move the black dot at a velocity v dot millimeter per second, that means you've already know the velocity of this. Then what will be the rotation, revolution per minute, right? Again, we just do the inverse way what we did on previous slides. So we have the velocity v dot millimeter per second, and we have 60 seconds per minute. Also, for each of a revolution, the pulley, the timing belt travels pi dp millimeter, and we put them together. It turns out that's the revolution per minute. Another thing is, because in this specific question, we assume the motor is directly attached to the pulley, but in many cases that could be the gears, right? So let's see, the motor is attached to our gear. And it has a gear ratio 3:1. That means when this smaller gear rotates 3 turns, this bigger one rotates only one turn. And this bigger one attached to the pulley, and also the timing belt. It turns out you need to figure out this after this is calculated. In this specific case, if this one rotates 1 turn, this will rotate 3. So you need to time 3, and that is the how many revolution of the motor have. Another question. If you want to move the black dot at distance x, then how many revolutions should you turn the motor, right? So we've already know the dot move this pi dp millimeter per revolution, and we know the distance is x millimeter. So if we use the x and divide and the x is divided by the pi dp, turns out you will have the revolution. Again, if there are gear system, you need to use the gear ratio to compute the final revolution accordingly. Sorry. So in the z-axis is a little different. Typically, a cantilever platform supported on one side. So as you can see here, there will be a platform attached in this direction. Let's see, and the motion will move up and down, right? And for the platform, there are spring-loaded screws, right? And because there are 4 different corners, but actually you do not need 4 springs, because 3 contact points determine a plane. So you only need 4 spring-loaded screws, and they are good enough. So we usually use the lead screws to drive the platform move up and down. And there's a concept called pitch. So the pitch is the distance between between the 2 neighboring teeth of the screw. if this rotation, if this is rotated one rotation, uh, basically this rod will travel up and up or down by by this distance, by the pitch distance, right? So there, it's quite similar for the screw uh, versus the pulley and the timing belt. So let's see, you have a pitch P. Oh, by the way, this pitch actually it has a unit millimeter per um, revolution. Even when you check the specification of this screw, it gives you millimeter back, but actually it means the millimeter per revolution. You need to use this in your calculation. Um, so you have a pitch P of a lead screw, and how many motor rotation are needed to move the knot a distance of x. So it, we could have, because we have one rotation for p millimeter, right? And then we have x as the distance to travel. Then put the two together, we will have the revolution. But you need to be careful. Here assume one, if the motor rotates one turn, this screw also moves one turn. So let's see, this is attached to a let's see, here is a pulley, and there's a belt attached to another big pulley, and this pulley is turns out attached to a motor, right? Again, you need to figure out um, similar to the gear ratio. You need to figure out how many turn this will be have if this rotation, if this has one rotation, and use this, you could figure out the rotation revolution of the motor should have. So if we have the pitch of a lead screw, and assume the screw is directly attached to a motor, that means there's no pulleys, no nothing. Then how should the motor speed if you want to move the knot at a velocity of v millimeter per minute? So what we want to have is this um, revolution per minute, right? We have the velocity v millimeter per minute, and we have this pitch, and we could put them together, and that is the revolution per minute. Again, if the motor is connected to screw via the timing belt and pulley, you need to figure out the ratio between the screw, the lead screw, and also the motor, and use that to apply to this answer, and it turns out that will be the one motor should rotate. So if we have all this calculated, it turns out we need to have a file to specify all the settings to the hardware, and what we have is the G code. So in many slicing software, the final output will be the G code, and the G code will align the XY coordinate of the printing cartridge as well as the XY coordinate of the next point you want to move. and such that you will have the um, uh, printing task performed successfully. So here shows the example of the G code, and just give you some ideas about these keywords. For example, the G0 means the rapid move, G1 means straight line move, and also there's some specification like the feed rate uh, uh, in the millimeter per second. Also the unit G20, but it could be changed for different 3D printers. You need to check their document to have a, more detailed understanding about the G code. Okay, let's see. Well, actually, we could do some calculation by having a lead screw with 60 thread per inch. Then you will have the pitch, right, using this. And this is connected to a step motor with a 1.8 step angle. You want to move a knot of distance. You want to move the knot a distance of 1.5 inches at a speed of 10 inches per minute. Then how many steps must the motor be turned? At what speed should the motor to be turned? This is the a calculation you need to use all the information you had in the previous slides, and that is what you eventually will do with the Arduino microcontroller, and that will run the 3D printer's step motor. So I will let you know to look at this first, and I will give you a solution afterwards. And you will have similar questions in your homework as well. So besides the Cartesian 3D printers, there are also other configurations like this delta and the polar ones. Let's look at this delta printer. So as you can see here, there are three bars, and by specifying the different motion along the three bars, you could move the printing head in the three-dimensional degrees. But all the computation, they are same as what we just described for the Cartesian-based 3D printers. And this one is a polar-based 3D printers.